forward for our discussion of aldehyde and ketone chemistry and the new material, we really have only one topic here left to discuss before we get to the carboxylic acid derivatives. But this is an important topic because this is a very useful reaction. And it's this reaction here that's known as the Wittig reaction. This is named after a German chemist named George Wittig, who won the Nobel Prize for this. I think it was in around 1919 or so, according to Wikipedia. And it's a very useful reaction because, as I mentioned in that short video, what it is it's a reaction to take a aldehyde or ketone, the carbonyl group, and convert it to an alkene here. So we're taking a carbon-oxygen double bond and changing it to a carbon-carbon double bond. So what this does is it really bridges two major aspects of the chemistry we've been discussing. In OChem 1, there was a lot of carbon-carbon double bond chemistry, electrophilic addition. You can have something over here like HBr and add something across that double bond. So there's all sorts of reactions with alkenes. What we've been seeing for the last 2 weeks is there's all sorts of reactions with these carbonyl groups here with aldehydes and ketones. So now we can actually work and generate an alkene from the carbonyl group. So this will be very useful in synthesis. So like the Grignard reaction came up a lot, the Wittig reaction is another very useful reaction. This reaction has a couple of new components to introduce though. And one is this reactive species, which is known as a Wittig reagent. In the most general sense. And then also this sort of a compound is actually an ylid. I don't know where the spelling came up from, but it's pronounced ylid, not yield. So this ylid is a species that has a negative and a positive formal charge on adjacent atoms. So when we look at this species here on the top, the carbon here has a negative formal charge, phosphorus has a positive formal charge. So this is an example of an ylid. 9 times out of 10, it'll be phosphorus, but we'll see in the one example is that it can also be sulfur. We'll come to this again as well. pH stands for phenyl here. So what we're going to do is take this ylid species, react this with a ketone, as shown here, a generic ketone like acetone, and introduce a carbon-carbon double bond. And this carbon here, I put C in the top to illustrate that this carbon here is the carbon that comes from this ylid species. So it's bringing 2 hydrogens with it, which in your product you'll have 2 hydrogens. And we can replace this later on with some alkyl group to introduce more structural diversity here. So an overall Wittig reaction actually has 3 components, and then we'll go through this here stepwise. But on the right here, I summarize that we might take something like this methyl bromide here, or bromomethane, and in step 1, we'll treat this with PPH3, which is triphenylphosphine, followed by this compound 2, which is N-butyllithium, and I'll write these out in a second, followed by our ketone. And in this 3-step process, we're taking and converting this ketone here into the alkene, and we're actually attaching the carbon and 2 hydrogens from this alkyl bromide. So this Wittig reaction consists of these 2 major parts. The first thing we need to do is actually to prepare what's known as this Wittig reagent. And this is a 2-step process. So let's stick with our bromomethane here. And we're going to react this with the PPH3. So I'll just draw it out the one time altogether. So this is 3 benzene rings. Which is normally abbreviated as triphenylphosphine, PPH3, triphenylphosphine. And this has a lone pair of electrons on the phosphorus. So this phosphorus is actually a nucleophile with that lone pair of electrons. So what it can do is it's going to attack, kick out the bromide, to form a species here that looks like this. Let's just collapse these phenyl groups down to pH. Make this look a little bit better. That looks like this. And what's important here is that in this first reaction, this is just a classic SN2 reaction. So our nucleophile triphenylphosphine is going to kick out bromide, an SN2 reaction to form this species here that we have on the right. Now, in the attacking here, the phosphorus uses its lone pair of electrons to form that bond with the carbon, so now the phosphorus has a positive formal charge. So we're halfway to our ylid, and now with this carbon having this positively charged phosphorus right next to it, it makes these hydrogens here a little bit more acidic. From OChem-1, the pKa of a sp3 hybridized carbon, it's around 48 to 50. We don't have to memorize this for here, but this pKa is around now 35 or so. So now what we can do is use a reagent like our organolithium that we've seen before, similar things at the beginning of the class. And this now is N-butyllithium. Which is going to act as a strong base. So this N here means normal, or a straight chain. It's not branched. Okay. So N-butyllithium. We use these organometallics like our lithium or our Grignard reagents as strong nucleophiles, but they're also strong bases. So we can think about this as a carbon minus lithium plus. There's no carbonyl group for this to attack, but instead what it can do is pull a proton off here and move these electrons up onto this carbon. So in deprotonating, make this bond a little bit bigger, we're going to end up with this is the same over here. Phosphorus has a positive formal charge, and now we're left with two hydrogens on here, and I'll just put the charge on the top. In this particular case, and then we'll also end up with this species, which will now have the hydrogen on it as well. And then we'll have lithium somewhere hanging around, but we don't really care about that. And now what we've done down here is we've generated our ylid. So this is going to be the important species in the reaction that we're going to use. And one thing I should mention about it, and I'll write it down here below, so I didn't save enough space here for the reaction, it looks like, is I'll rewrite this. And let's just collapse this down to pH3 to save some space. Negative formal charge, positive formal charge. This is one thing I think that's oftentimes quite confusing, because let's first write a resonance structure that we could write. We could move these electrons down here to form a double bond. Form this species. And that seems like a legitimate resonance structure, and indeed it is. And if we were to look back at all of our notes from OChem-1, when we're evaluating different resonance structures, we would see that what makes a major contributor in a resonance series of resonance structures would be something maybe that has a full octet of electrons in all the atoms. We want to minimize formal charges. We want to keep oppositely charged formal charges away from each other. However, in this particular case, actually, this species seems to be the major contributor, and this one seems to be the minor. And this is counterintuitive to everything that we saw when we were first looking at other resonance structures. And it's a bit of a detail, however, it suggests that this is the main species which is going to be involved in the reaction. And a reason for this is oversimplified, is that the orbital overlap of carbon and phosphorus here is quite poor. So if I were to point at some random periodic table, you would see where they're located. And that for phosphorus, the orbitals that would be involved in a resonance hybrid, it's much bigger, and it's not going to really overlap with the carbon, which as a result then is going to keep this negative charge, this lone pair, more localized on the carbon. And so that's why now, rather than dealing with oxygen or nitrogen or other carbons as most resonance structures we've dealt with, now we're dealing with phosphorus. So we can think about this negative charge residing pretty much solely on this carbon. So that's why it seems weird saying that this is the major contributor, but there seems to be a structural explanation for this. Okay, so now we've made our Wittig reagent. So here we made the Wittig reagent, or the ylid in the general case. So now let's do something with it. So in the next step, so I just went right through strong base, but hopefully that's okay here. So now we're going to carry out the actual Wittig reaction. And this one, we just want to draw things in an appropriate sense so everything lines up. So let's take our ketone. I'm going to make it larger here. Let's fill up the space. Which in this case is acetone. And now, just like what we've seen before, remember with all this carbonyl chemistry is that this carbon is electrophilic, just like on the exam. And then we have all these lone pairs of electrons and this electrons-rich double bond here with this oxygen. So the way this likely happens is that we'll put PPH3 here, triphenylphosphine component, and then here is our two carbons. And so carbon and two hydrogens. Deal with our formal charges, plus and minus. And current evidence suggests that this reaction is happening all at once, and so that the carbon is going to act as a nucleophile, attacking the carbonyl carbon. Simultaneously, the electrons in this carbon-oxygen double bond are going to form a bond to the phosphorus. This will end up forming a species that has a four-membered ring. So let's form a bond from the carbon to the other carbon, put our two alkyl groups down below, and form a bond to our phosphorus, PPH3. These are still bonded together. So this gives us an intermediate. This is known as an oxyphosphatane. And now we need to somehow form our carbon-carbon double bond. And what can happen is that the electrons in this carbon-phosphorus bond, we're going to break that bond and use those electrons to form our carbon-carbon double bond. However, if that were the only thing that could happen, we'd have too many bonds in this carbon here. So what we're going to do is break this carbon-oxygen bond and use that to form a phosphorus-oxygen double bond, all simultaneously. So what this leaves us with is this carbon here bonded to these two methyl groups. Now it's going to have a double bond to that species, that's CH2. I'll put the carbon there to help show it. And then on the other side, so that's this bottom part here, then we're going to end up with PPH3 with a phosphorus oxygen double bond. Let's just put the pHs out here. And this species, this is triphenylphosphine. Phosphorus oxide. And this is a major driving force in the reaction. It's actually forming this species that we have here. And then, I'm going to do blue here. Here's our alkene of interest. So to review the steps of this reaction here, we're going to take our ylid, our Wittig reagent here, which has those adjacent formal charges. All in one step, we're going to have the carbon act as a nucleophile attacking the carbonyl carbon. The phosphorus is acting as the electrophile, picking up electrons from this carbon-oxygen bond, forming this four-membered intermediate, this oxyphosphatane. And then this is going to break down, breaking the carbon-phosphorus bond to form the carbon-carbon double bond, the new alkene. And then this carbon-oxygen bond is going to break, forming a phosphorus-oxygen double bond.